As a research charity, cool science always gets us excited. But the tech that yesterday earned its pioneers this year's Nobel Prize in Chemistry is so cool it's sub-zero cryo-electron microscopy. Far from the microscopes we used in school to examine strands of our hair and the features of onion skins, this form of imaging has allowed researchers to picture the molecules of life in detail previously inconceivable. Central to the technique's prying is getting its subjects cold. Very cold. And these frigid microscopes are helping researchers make real progress in cancer science. It works by bombarding samples with a powerful beam of electrons, tiny particles that spin around the hearts of atoms. The beam is so strong that it was believed this technique, called electron microscopy, could only be used on dead or non-living things because of the damage it caused to biological molecules. This, on the whole, isn't ideal when the goal is to get a picture of the molecules of life itself. This is where one of the Nobel laureates, Dr. Richard Henderson from the MRC Laboratory of Molecular Biology, Cambridge, comes in. He was the first to use electron microscopy to capture a 3D image of a protein, the molecules that our DNA contains the recipes for. I am delighted for everybody in the field that the Nobel Prize for Chemistry has been awarded to acknowledge the success of cryo, he says in a statement about the award. But Henderson wouldn't have made that crucial advance without the other two laureates. Over the course of almost a decade, Professor Joachim Frank, from Columbia University in the US, worked out how to merge 2D images into crisp 3D versions. Also working in the 1980s, Professor Jacques Dubochet, from the University of Lausanne in Switzerland, found that rapidly cooling the samples in water allowed them to maintain their shape. Together, this trio has opened our eyes to a microscopic realm that's helping scientists better understand the molecular workings of the world of biology, from bacteria to cancer cells. We spoke to two experts using the technique to study cancer to find out why it's so exciting. The devil isn't in the detail. The ability of cryo to essentially freeze biological molecules in time is helping researchers understand what's going right and wrong inside cancer cells. Cryo is exciting because it allows us to study the structure of biological molecules that we previously weren't able to in incredible detail, says Professor Richard Bayliss, a cancer research and structural biology expert from the University of Leeds. This helps us understand how they work, but also to study those that are faulty in cancer. By giving us insight into what's happening at the molecular level, we can develop ideas on how we can design drugs to precisely block these faulty molecules. That'll be a major achievement. Before cryo came on the scene, achieving such a level of detail was tricky. Previously, the field of structural biology has been driven primarily by one microscopy technique, X-ray crystallography, says Professor Lawrence Pearl, a cancer research and structural biologist from the University of Sussex. It's very powerful, but it's a challenging and unpredictable technique. It's also limited in its ability to study fully assembled biological machines as they work in the cell. It's like being able to study just the engine of a car, but not how this integrates with the rest of the parts. This is where cryo comes in. Now we have the ability to look at the big biological machines and the state that they operate in cells, and understand how they function, and how that function is altered by genetic faults in cancer, Pearl says. This understanding of structure and function speeds up our ability to discover and design new cancer drugs. For now, the hefty multi-million-pound price tag of state-of-the-art machines capable of capturing the highest levels of molecular detail means they aren't too widely available to scientists. And this limited access has meant that the capabilities of cryo have yet to be fully realized. But that's something that Bayliss sees as an opportunity. Once more people have their hands on this technology, we'll find a lot more applications for it, he says. It's allowing us to be more ambitious about the kind of work we can do and start projects we couldn't have thought of before. It's exciting to see what's happening. Justine more on this topic.